Introduction to Remote Sensing. Remote sensing can be defined as the science and art of obtaining information about an object, area, or phenomenon through the analysis of data acquired by a device that is not in contact with the object, area, or phenomenon under investigation. Therefore, the sense of sight is considered a tool for remote sensing, as is the sense of hearing, just as the camera and binocular vision are considered remote sensing, and any method through which information can be obtained without direct contact with the target is considered remote sensing. For example, if we see a cup of tea and see steam rising from it, we realize that the teacup is hot, and this is considered remote sensing, as we have obtained information that the tea is hot without touching the teacup. But if you hold the teacup and feel the heat with your hand, this is not considered remote sensing. Imaging is considered the most widespread method of remote sensing, as it is possible to be carried out in different light ranges through cameras installed on the surface of the Earth. It is also possible to be carried out from close altitudes using cars, by flying, using a space shuttle, or by using the most common method, which is satellites. Satellite remote sensing data is usually the most accurate and up-to-date map available of developing countries. Especially with fast-growing towns and cities in developing countries, it is practically the only method that can follow up the urban growth. Currently, high-resolution satellite images are available that show features of the Earth's surface with high resolution. In comparison with the aerial survey, satellite remote sensing offers some advantages. Easy monitoring of wide areas. Availability of digital and multispectral data. Survey of areas logistically difficult to reach or where the organization of photogrammetric flights is hard. Digital data gathered by a satellite sensor can be transmitted over radio or microwave communications links and stored on magnetic tapes, so they are easily processed and analyzed by a computer. Many satellites orbit the Earth, so the same area can be covered on a regular basis for change detection. Once the satellite is launched, the cost for data acquisition is less than that for aircraft data. Satellites have stable geometry, meaning that there is less chance for distortion or skew in the final image. Elements of remote sensing. 1. Energy source or illumination. The first requirement for remote sensing is to have an energy source, which illuminates or provides electromagnetic energy to the target of interest. 2. Radiation in the atmosphere. As the energy travels from its source to the target, it will come in contact with and interact with the atmosphere it passes through. This interaction may take place a second time as the energy travels from the target to the sensor. 3. Interaction with the target. Once the energy makes its way to the target through the atmosphere, it interacts with the target depending on the properties of both the target and the radiation. For recording of energy by the sensor, after the energy has been scattered by, or emitted from the target, we require a sensor, remote not in contact with the target, to collect and record the electromagnetic radiation. 5. Transmission, reception, and processing. The energy recorded by the sensor has to be transmitted, often in electronic form, to a receiving and processing station where the data are processed into an image, hard copy and/or digital. 6. Interpretation and analysis. The processed image is interpreted, visually and/or digitally or electronically, to extract information about the target, which was illuminated. 7. Application. The final element of the remote sensing process is achieved when we apply the information we have extracted from the imagery about the target in order to better understand it, reveal some new information, or assist in solving a particular problem. Basic physical principles of remote sensing. Electromagnetic spectrum. All matter with a certain temperature radiates electromagnetic waves of various wavelengths. The total range of wavelengths is commonly referred to as the electromagnetic spectrum. It extends from gamma rays to radio waves. Remote sensing operates in several regions of the electromagnetic spectrum. The optical part of the electromagnetic spectrum refers to the part of the electromagnetic spectrum in which optical laws can be applied. These relate to phenomena, such as reflectance and refraction that can be used to focus the radiation. the optical range extends from X-rays, 0.02 micrometers, through the visible part of the electromagnetic spectrum up to and including far infrared, 1000 micrometers. The visible region of the spectrum is commonly called light. It occupies a relatively small portion of the electromagnetic spectrum. It is important to note that this is the only portion of the spectrum that we can associate with the concept of color. Blue, green and red are known as the primary colors or wavelengths of the visible spectrum. The longer wavelengths used for remote sensing are in the thermal infrared and microwave regions. Thermal infrared radiation gives information about the surface temperature. Surface temperature can be related, for example, to the mineral composition of rocks or to the condition of vegetation. Microwaves can provide information on surface roughness and surface properties such as water content. Energy interactions with Earth's surface materials. There are three forms of interaction that can take place when energy strikes or is incident upon the surface. These are absorption, transmission, and reflection. The surface reacts to the total energy incident on it in one or more of these three ways. The proportions of each will depend on the wavelength of the energy and the material and condition of the feature. Applying the principle of conservation of energy, the relationship can be expressed as incident energy equals reflected energy plus absorbed energy plus transmitted energy. Absorption occurs when radiation energy is absorbed into the target. Transmission occurs when radiation passes through a target. Reflection occurs when radiation bounces off the target and is redirected. This part explains why we see things in the colors they are. When electromagnetic energy is incident on any feature of the Earth's surface, such as leaves, various fractions of energy get reflected, absorbed, and transmitted. Chlorophyll strongly absorbs radiation in the red and blue wavelengths but reflects green wavelengths. Leaves appear greenest to us in the summer when chlorophyll content is at its maximum. In autumn, there is less chlorophyll in the leaves, so there is less absorption and proportionally more reflection of the red wavelengths, making the leaves appear red or yellow. Yellow is a combination of red and green wavelengths. The internal structure of healthy leaves acts as excellent diffuse reflectors of near-infrared wavelengths. If our eyes were sensitive to near-infrared, trees would appear extremely bright to us at these wavelengths. In fact, measuring and monitoring the near-IR reflectance is one way that scientists can determine how healthy or unhealthy vegetation may be. Digital camera. The image is formed in the digital camera by recording the reflection force arriving from the surface of the Earth and passing through the lens to a group of sensors in the focal plane of the lens, where each sensor covers an area of the Earth's surface, and the area on the Earth corresponding to the sensor is expressed in terms of spatial resolution. Digital image. Each sensor records only one value, and therefore what is recorded in the camera is a matrix of the value of the reflection strength arriving from the surface of the Earth. This matrix of values is displayed in a gradient of gray, and thus a person can distinguish the image with different features such as roads, buildings, and plants. In remote sensing, reflection can be recorded in a specific range of the spectrum, such as recording light reflected in the red range only, green only, and blue range only. As we said, the digital camera records the strength of the reflection reaching it in these ranges as numbers, and to be identifiable, these numbers are converted into grayscale degrees, and therefore the output image in any range is a set of numbers displayed in a gradient of gray. It is possible if we display the reflection arriving from the surface of the Earth in the range of red light in a gradient of red, and display the reflection arriving from the surface of the Earth in the range of green light in a gradient of green, and display the reflection arriving from the surface of the Earth in the range of blue light in a gradient of blue, then we combine the value of the three colors, and then we can see images in color as the eye sees them. the eye sees reflection in the range of blue, green, and red. Remote sensing is characterized by being able to image in ranges of light that the human eye cannot see, such as infrared rays and thermal rays. Therefore, if we have an image of the reflection of the Earth's surface in the infrared range, these rays cannot be sensed by the eye. With it, we will see in the image a reflection that the human eye does not see, but it can be recorded by the image. This is the advantage of remote sensing, which is recording and displaying what the eye does not see. So if we have a recording of the reflection of the Earth's surface in infrared rays and we display it in a gradient of red, and the reflection in the red range and we display it in the gradient of green and the reflection in the green light range, and we showed it in the gradient of blue, we will see the same previous image, but in a different way, as we will see the infrared reflection of the plants in the image in red. Here we see two images of the same place. In the image above, the reflection recorded in the blue, green, and red range was combined so that the image was displayed in the way that the human eye distinguishes. We see an image of an area with plants, buildings, roads, and a sports stadium. In the image below, the infrared, red and green range were combined. Thus we see the plants that were in the image above in green are shown in red, where the red color is a recording of infrared reflection. As previously mentioned, plants reflect in infrared rays, but the human eye cannot distinguish this reflection, and we notice here that the playing field is still in green. It did not become red like the rest of the plant. This is because the floor of this stadium is artificial grass, and it does not reflect infrared rays like plants, and therefore in remote sensing we were able to obtain information that we were not aware of with normal vision. Energy interactions with Earth's surface materials. In the early days of remote sensing, it was believed that each Earth's surface material had its own unique distribution of reflected, emitted, and absorbed radiation. These spectral characteristics can be used to distinguish one thing from another or to obtain information about shape, size, and other physical and chemical properties. The figure depicts how the three dominant Earth surface materials of soil, vegetation, and water reflect the sun's energy in the visible infrared range of wavelengths. It was found that water reflects about 10% or less in the blue-green range, a smaller percentage in the red, and certainly no energy in the infrared range. Should the water contain suspended sediments or should the clear water body be shallow enough to allow reflection from the bottom, then an increase in apparent water reflection will occur, including a small but significant amount of energy in the near-infrared range. This is a result of reflection from the suspension or bottom material. In the left image, we can see a recording of the reflection of the Earth's surface in the green light range, and in the right image, we can see a recording of the reflection of the Earth's surface in the same place as the image on the left, but in the infrared range. As we see in the images on the right, a black stripe, which is a river passing through the area, and it is visible in the images because water does not reflect in the infrared range, and therefore the reflectance value recorded in the image in the infrared range is close to zero, and thus it appears in the image in black, while water is not clear in the image in the green range. And thus water bodies can be distinguished well in the infrared range in mapping it by separating near-zero reflectance values from the rest of the image. Soils have a reflection that increases approximately monotonically with wavelength, however with dips centered at about 1.4 micrometers, 1.9 micrometers, and 2.7 micrometers owing to moisture content. These water absorption bands are almost unnoticeable in very dry soils and sands. In addition to these bands, clay soils also have hydroxyl absorption bands at 1.4 micrometers and 2.2 micrometers. The vegetation curve is considerably more complex than the other two. In the middle infrared range, it is dominated by the water absorption bands at 1.4 micrometers, 1.9 micrometers, and 2.7 micrometers. The plateau between about 0.7 micrometers and 1.3 micrometers is dominated by plant cell structure, while in the visible range of wavelengths, it is plant pigmentation that is the major determination. In remote sensing, we are most interested in measuring the radiation reflected from targets. There are two types of reflection, which represent the two extreme ends of the way in which energy is reflected from a target: specular reflection and diffuse reflection. When a surface is smooth, we get specular or mirror-like reflection where all, or almost all, of the energy is directed away from the surface in a single direction. Diffuse reflection occurs when the surface is rough and the energy is reflected almost uniformly in all directions. If the wavelengths are much smaller than the surface variations or the particle sizes that make up the surface, diffuse reflection will dominate. For example, fine-grained sand would appear fairly smooth to long-wavelength microwaves but would appear quite rough to the visible wavelengths. Active and passive remote sensing. At the beginning of the explanation, we talked about the elements of remote sensing, and the first element is the lighting source. The sun provides a very suitable source of energy for remote sensing. The sun's energy is reflected, as is the case with visible wavelengths, or is absorbed and re-emitting, as is the case with thermal infrared wavelengths. Remote sensing systems that measure naturally available energy are called passive remote sensing. Passive remote sensing techniques employ natural sources of energy, such as the sun. While active remote sensing techniques, for example, radar and laser, have their own source of energy. Active sensors emit a controlled beam of energy to the surface and measure the amount of energy reflected back to the sensor. The best example of active and passive remote sensing is the use of the camera, where when imaging the rays reflected from the body, which falls on it from the sun, this type is called passive remote sensing, where the light reaching the camera is not from the camera but from the sun. Whereas if the camera's flash was used in imaging, the light emitted from the camera will fall on the object and then be reflected back to the camera to be imaged. In this case, this type becomes active remote sensing, as the image was the result of energy emanating from the camera. Passive sensor systems based on the reflection of the sun's energy can only work during daylight. Passive sensor systems that measure the longer wavelengths related to the Earth's temperature do not depend on the sun as a source of illumination and can be operated at any time. Passive sensor systems need to deal with the varying illumination conditions of the sun, which are greatly influenced by atmospheric conditions. The main advantage of active sensor systems is that they can be operated day and night and have a controlled illuminating signal. Satellite characteristics. The target of the satellite mission is to acquire the largest number of images with the best quality and the best area coverage. 1. Satellite orbits. The first characteristics of satellites are satellite orbits, where satellites rotate in a fixed orbit at different altitudes. The path followed by a satellite is referred to as its orbit. The lower the orbit, the better the imaging resolution, however the smaller the swath width and the shorter the satellite lifetime. The first type of orbit is geostationary orbit, which is an orbit located at a very high altitude. The satellites in this orbit view the same part of the Earth's surface at all times, and they have geostationary orbits. In this type of orbit, the satellite rotates at a speed that matches the Earth's rotation speed, so that it appears fixed relative to the Earth's surface. Therefore, anyone standing on the ground watching the satellite would notice that the satellite is fixed in its place relative to the Earth. The value of the semi-major axis is about 42,170 kilometers, so the geostationary satellite is located approximately 35,800 kilometers above the equator. Such orbits are used for geostationary meteorological satellites as well as for telephone and television relay satellites. The second type of orbit is low Earth orbit. This type of orbit contains most of the remote sensing satellites, and they are at an altitude ranging between 300 kilometers and 1,000 kilometers. This choice represents a compromise between the necessity of close observation of the Earth and the lifetime of the satellite. Low Earth orbit, improving the potential spatial resolution with respect to what can be achieved from a geostationary orbit, at the expense of reduced coverage. The useful range of orbit altitude for low Earth orbit satellites is constrained by the Earth's atmosphere and by Van Allen belts. If a satellite orbits too low above the Earth's surface, it will experience an unacceptably high degree of atmospheric friction and will spiral out of its orbit and toward the Earth. The Van Allen belts are rings of high-energy, charged particles, mostly electrons and protons, in the Earth's equatorial plane, at altitudes between about 2,000 and 5,000 kilometers and between 13,000 and 19,000 kilometers. They have probably been captured from solar wind by Earth's magnetic field. Most of the remote sensing satellite platforms today are in near-polar orbits for meteorological and geophysical applications. This means that polar orbiting satellites closely parallel the Earth's meridian lines. They pass over the north and south poles each revolution. Most satellites with near-polar orbits have altitudes ranging from 600 to 800 kilometers, with orbital periods of 98 to 102 minutes. Sun-synchronous orbit. Synchronous orbit. In this orbit, the satellite passes over each area of the Earth's surface at a constant local time of day called local solar time. To achieve this condition, the orbit cannot exactly follow a true north-south track to go over the poles. In synchronous orbit, the angle between Earth-Sun direction and the orbit plane is constant and the satellite flies over a certain area approximately at the same local time with the same conditions of light. Actually, the orbit must be slightly tilted towards the northwest with a steep inclination angle of about 98 degrees. With the Sun-synchronous orbit, at any given latitude the position of the Sun in the sky as the satellite passes overhead will be the same within the same season. This is an important factor for monitoring changes between images or for mosaicing adjacent images together, as they do not have to be corrected for different illumination conditions. We find that the difference between the polar orbit and the Sun-synchronous orbit is that the polar orbit follows a fixed path between the north and south poles, while the Sun-synchronous orbit is slightly tilted, with an inclination angle of about 98 degrees. The second characteristic of satellites is the path of the satellite, ascending and descending passes. The term ascending passes of the orbit corresponds to that portion of the orbit when the satellite is moving from south to north. Descending passes of the orbit correspond to north to south movement. Most sun-synchronous polar orbits pass from north to south, descending passes, over the sunlit hemisphere and return from south to north, ascending passes, over the nighttime hemisphere. In other words, the ascending pass is on the shadowed side of the Earth while the descending pass is on the sunlit side. Sensors recording reflected solar energy only image the surface on a descending pass when solar illumination is available. Some satellites that contain active sensors that provide their own illumination or passive sensors that record emitted, e.g. thermal, radiation can also image the surface on ascending passes. The third characteristic of satellites is ground swath width or the width of the area imaged by the satellite. As the satellite rotates around the Earth, the sensor imaging a specific part of the Earth's surface. The width of the imaged area on the surface is referred to as ground swath width. The closer the satellite is to the surface of the Earth, the smaller the width of the imaging area covered by the satellite, but with high spatial resolution, and the higher the satellite's orbit is, the larger the width of the imaging area is, but with low spatial resolution. The fourth characteristic of satellites is the transfer of data from the satellite to the Earth's surface, and this is done through three methods. The first method is that the satellite is within range of the ground receiving station and is therefore able to send data directly from the satellite to the ground station. In the second method, if the satellite has an internal storage unit, meaning that after the satellite captures a set of images, it can keep the images inside its storage unit and wait until it is within range of the ground receiving station and thus sends the stored data directly to the receiving station. In the third method, the satellite sends data to another satellite, which can be sent to a third one, and so on until it reaches a satellite that is within the receiving range of the ground station and thus is able to transmit data. This depends on the capabilities of the company that owns the satellite. Therefore, if the satellite does not have an internal storage unit, it cannot capture images and transmit data outside the receiving station's range area. Or if it does have a storage unit, This will allow it to capture a limited amount of images in a location far from the receiving station and wait until return at a later time to send the data to the receiving station. The last case is in companies with very high capabilities that own a group of satellites so that the satellite can capture it anywhere in the world and transmit data at the same time to its receiving stations via its group of satellites. To send a signal directly to the ground means that the satellite has to be above the horizon as seen from a ground receiving station. In high-latitude areas, the ground receiving station will be visited by satellite more frequently as the orbit paths converge near the poles. The coverage area of a receiving station is geometrically limited by the line of view between the ground antenna and the satellite. If a satellite does not have a registration system on board, the coverage area corresponds to the coverage areas of the receiving stations. Satellite imaging systems. There are several satellite imaging systems, but we will explain the two most common satellite imaging systems. The first system is the Whiskbroom Scanner, which is also referred to as a crosstrack scanner, and it is similar to the panoramic imaging system in aerial surveying. This method is the first method that was used in imaging on the first remote sensing satellite, which was the Landsat one in 1972. In this type, a rotating mirror is used to scan the Earth's surface from one side to the other in a manner perpendicular to the direction of the satellite's movement, where the reflected image is directed to a lens and the lens faces the sensor. This means that I have a sensor, lens, and mirror, and the mirror is rotated, so it reflects the surface of the Earth from the right to the left, towards the lens, and the lens aims the reflection in the direction of the sensor, and the sensor senses the reflection reaching it, records it, empties its memory, and then begins recording the second reflection after it. Thus, in one movement of the mirror from the right to the left, the satellite will have captured a group of successive images side by side, which together form a row from the image. In the case of the Landsat 1 satellite, it will be 80 meters wide and 185 kilometers long, then it will be the second row of the image, and so on, and then the rows of images beside each other will form a large image. Whiskbroom scanners have an advantage of over other types of sensors is that they have fewer sensor detectors to keep calibrated. The major disadvantage of such a system is the presence of moving parts and the low detection or dwell time for each pixel. The well-known examples of Whiskbroom images are the Multispectral Scanner, MSS, carried on Landsat 1-5, the Thematic Mapper, TM, carried on Landsat 4-5, the Enhanced Thematic Mapper Plus, ETM Plus, carried on Landsat 6-7. The second type of imaging method is the Pushbroom Scanner method. This system consists of a group of sensors adjacent to each other. This system is similar in its operation to the way the strip camera works in aerial surveying, where a strip of the Earth's surface is imaged, and thus, with the movement of the satellite, a group of strips are imaged. The first satellite launched with this system was the French satellite Spot 1 in 1986. This satellite had a strip consisting of 6,000 sensors with a resolution of 10 meters beside each other for each spectral band, and the strip was placed in the focal plane of the optical system. This row, which contains 6,000 sensors, will be placed perpendicular to the direction of the satellite's movement and will move with the satellite, and thus it will image a strip of the Earth's surface 10 meters wide and 60 kilometers long, 10 meters wide because the resolution of the sensor is 10 meters by 60 kilometers because we multiply 10 meters by the number of sensors in the row, so 10 times 6,000 equals 60 kilometers. Therefore, the length of the sensor array determines the width of the imaged area. With the movement of the satellite, it records successive images 10 meters wide, 10 meters wide, and 10 meters wide 6,000 times until the image is 60 kilometers wide and 60 kilometers long. Each sensor records one number, which is the strength of the reflection reaching the sensor in a specific spectral range. The brighter the signal, the higher the recorded value. The laws followed in remote sensing are very similar to the laws followed in photogrammetry, but with slightly larger dimensions, meaning in satellites, the speed of the satellite is approximately 7.5 kilometers per second, and therefore the imaging speed is much higher and therefore requires an imaging system with higher characteristics than it is found in aerial photogrammetry, but it has the same physical rules. The focal length is f, the flight height, h, the distance on the image, which represents the pixel dimensions px and py, and the corresponding distance to it on the surface of the Earth, x, or I. The time the system needs to obtain one row in the image is called the integration time. The time interval between imaging rows is usually chosen equal to the integration time. The integration time can be calculated using the relationship delta Ts equals ph over Vf, where delta Ts is the integration time, p is the sensor dimension, h is the satellite height, v satellite speed, and f focal length. An example of how to calculate the integration time in satellites operating with the Pushbroom system in the case of the Spot 5 satellite. In the case of Spot 5 satellite nadir viewing, a square, orthogonal grid with a sampling interval of 5 meters is generated. Considering the following characteristics. The number of sensors in the row is 12,000 sensors. This means that I have 12,000 sensors next to each other on the strip, and each sensor is 651 micrometers. Focal length f is 1.082 meters, satellite height is 832 kilometers, satellite speed is 6.6 kilometers per second. Calculate the integration time. In this case, the integration time will be equal to delta Ts equals p multiplied by h over v multiplied by f equals 6.510 times 10 power of minus 6 times 832 times 10 power of 3 over the flight speed is 6.610 10 power 3 meters, and the focal length is 1.082 meters. We will find that the integration time is equal to 0.7521 times 10 power of minus 3 seconds, which means approximately 1 over 1330 of a second. At this time, the satellite will take an image of the strip, which is 12,000 pixels next to each other. These 12,000 pixels are a line in the image, and with a group of lines imaged, one after the other, in this case, creates a complete image. One of the disadvantages of the Pushbroom approach is that very long arrays are necessary to achieve a large ground swath. For example, the Spot ground swath is only 60 kilometers, compared to Landsat's 185 kilometers. The Spot system overcomes this limitation by using an across-track pointing mirror which allows it to look up to 31 degrees to the left or right of the nominal ground track. This also allows it to use data from multiple orbits for stereoscopic coverage. The Pushbroom approach has the distinct advantage in satellite operation of having no movable parts. This increases the expected lifetime and may reduce power requirements. The Pushbroom detector technology, however, is far more sophisticated than the Whiskbroom approaches. Currently, most satellites operate on the Pushbroom system. Satellite image characteristics. Each type of satellite data offers specific characteristics that make it more or less appropriate for a particular application. In remote sensing, there are 4 types of resolutions to be considered. The first type of resolution is spatial resolution. Spatial resolution is the minimum ground area observed by the instrument from a fixed altitude at a fixed moment. It is measured as the size of a pixel on the ground. The spatial resolution of the satellite image can be classified as less than 1 meter, very high, 1 to 5 high, 5 to 20 mean, 20 to 50 low, greater than 50 meters, very low. The spatial resolution of the sensor in the first remote sensing satellite Landsat 1 was 80 meters by 80 meters, and therefore on the Earth 80 meters could cover a house, a street, and a piece of agricultural land. All the 80 meters by 80 meters will be recorded in the image as 1 pixel with 1 number, so no details will appear clearly. It will show desert areas in general, agricultural areas in general, and residential areas in general. it was not able to provide the precise details. Then in 1986, the Spot 1 satellite was developed with a resolution of 10 meters. And as we see, 10 meters began to show higher details than the 80 meters. Then the resolution developed in 1999 and became 1 meter with the Ikonos satellite, and this is what appeared here. Currently, the resolution is 0.5 meter and 1/4 meters. Here we are talking about commercial satellite images that are available for purchase from companies and on the internet. It is certain that military satellites have a higher resolution than commercial ones. If we compare the appearance of the images with a resolution of 50 centimeters by 50 centimeters to the images at the beginning with a resolution of 80 meters by 80 meters, we would not be able to see any details. The second type of resolution is radiometric resolution. Radiometric resolution refers to the dynamic range or number of possible data file values in each band. This is referred to by the number of bits into which the recorded energy is divided. The radiometric resolution is expressed by the number of bits used to quantize a pixel. For each bit, it records an exponent of power of 2. For an 8-bit sensor, the digital values available are 256, from 0 to 255, where 0 represents the black and 255 the white. As we explained previously, the satellite image is a matrix, such as an Excel matrix, containing numbers, each number expressing the strength of the reflection coming from the Earth's surface. Example 4. A digital image has a radiometric resolution of 6 bits. What is the largest number that can be found in the image? 2 power 6 means 64, a gradient of gray that the sensor can distinguish. The number of values in a 6-bit image would be equals 64. Since the range of values displayed in a digital image normally starts at 0, in order to have 64 values, the maximum value possible would be 63. Therefore, the numbers in the image will have a range from 0 to 63, where from 0 to 63 is 64 numbers that the satellite sensor can distinguish. To clarify the radiometric resolution further, if we compare two images, the image above has a radiometric resolution of 8 bits, while the image below has a radiometric resolution of 2 bits. 8 bits means 256, which means 256 a gradient of gray, meaning the sensor can show or record reflections in 256 degrees, ranging from 0 to 255. The second image 2 bits means 4 degrees, which means from 0 to 3, which means 0, 1, 2, 3. Therefore, in this case, we can see the image is less clear than the one above, as the gradient of gray has become less in the image below. The third type of resolution is the spectral resolution. Spectral resolution refers to the specific wavelength intervals in the electromagnetic spectrum that a sensor can record. Wide intervals in the electromagnetic spectrum are referred to as coarse spectral resolution, and narrow intervals are referred to as fine spectral resolution. There are 3 main types of spectral resolution. The first type is the panchromatic sensor. This type of sensor distinguishes the parts of the light in blue, green and red together, meaning it senses the extent of the visible spectrum, although it is only one thing. The second type is a multispectral sensor. In this type, the sensor can distinguish a smaller part of the spectrum, such as the blue color range alone, the green color range, the red color range, the infrared rays range, and so on. Each band of them is called a spectral band, and there is more than one band in the satellite. Each band distinguishes a specific part of the spectrum, and therefore, its accuracy in identifying a specific part of the spectrum is higher than that of panchromatic, and the images resulting from it can be combined to display images in a different order to clarify objectives. The third type is hyperspectral. In this type, we can distinguish a very small part of the spectrum range, less than the multispectral, and therefore the image may contain more than one band, and sometimes it reaches thousands of bands. The 3 types that we talked about in spectral resolution, panchromatic, multispectral, and hyperspectral. Each of them can distinguish a specific range of the spectrum. Panchromatic is considered the lowest spectral resolution because it collects light from a very large range of the spectrum. In this case, it is possible to record the reflected image from a small area on the Earth, and thus the spatial resolution is high. The second type, multispectral, collects light from a smaller spectrum range than panchromatic, and therefore we need a larger area on the Earth corresponding to it than panchromatic so that it can collect enough light to form the image, and thus its spatial resolution is less than panchromatic. The hyperspectral has the highest spectral resolution because it collects light from a very small spectrum range, much less than the multispectral. It needs a very large area of Earth to collect the reflected light, and its spatial resolution is the lowest. This means that we are talking about an inverse relationship between the spectral resolution and the spatial resolution. Whenever the spectral resolution covers a small part of the spectrum, whenever a large area of the Earth's surface is needed so that light can be collected from it, this means that the spatial resolution is low, and the opposite when the spectral resolution is cover a large part from spectrum it can be collected from a small area of the Earth's surface, which means high spatial resolution. A group of different multispectral reflectance data is displayed together so that the data is displayed more clearly. We find, for example, that the QuickBird satellite can image in the panchromatic range in multispectral images in 4 bands of blue, green, red, and infrared. In the panchromatic image on the left, in which the sensor records the reflection in the blue, green, and red spectrum at the same time, its ability to distinguish a specific part of the spectrum is weak, but in this case, it can collect a large amount of light in this large range from a small area in the Earth, so we find that its spatial resolution is 0.6 meters, while the image in the middle is the multispectral image. We can collect the reflection in the blue band alone, the green band alone, the red band alone, and the infrared band alone, with a spatial resolution of 2.4 meters. Thus, the image can be merged to see the image in color. So in this case, we have in the satellite a panchromatic image with a very high spatial resolution of 0.6 meters and a color image with a low spatial resolution of 2.4. To benefit from the high spectral resolution in the multispectral and the high spatial resolution in the panchromatic image, the 0.6 meter image is merged with the 2.4 meter image in a process called pan-sharping, so that we convert the multispectral image to have a spatial resolution like the spatial resolution in the panchromatic image. It means a color image with a resolution of 0.6 meters at the same time. This topic will be explained in detail in the section on digital image processing. The fourth type of resolution is temporal resolution. Temporal resolution, also known as revisit period, refers to the temporal frequency at which the same ground area is sensed consecutively by the same sensing system. The interval of time required for the satellite to complete its orbit cycle is not the same as the revisit period. One method of refining the temporal resolution of satellite data is to tilt the scanning mirror of the sensing system. The temporal resolution of the same satellite varies with the latitude of the geographic area being sensed. This type of resolution is very important in studying the change in spectral characteristics of features over time. These changes can be detected by collecting and comparing images over successive periods. Change detection applications include, for example, monitoring the spread of oil spills and the impact of floods and earthquakes. Stereo acquisition. It was previously explained in aerial photogrammetry about how to obtain a three-dimensional view by having an overlap area between two images of the same place that were taken from two different places. This matter can also be applied through satellites in two different methods. The first method is a cross-track and the second is called long-track. In a cross-track mode, the two images are acquired from two different orbits. In this configuration, the time difference between the two acquisitions can be in the order of days or more. In a long-track mode, the two images are acquired from the same orbit with a time delay in the order of seconds. In the cross-track, the satellite turns in its orbit and takes an image, and then, when it turns again in another orbit, it takes an image of the same place again. In the second type, long-track, the satellite can capture images behind, below, and in front of it in the same orbit. Thus, all images from different angles are taken in the same orbit. If we compare the cross-track and the long-track, we find that the long-track is better than the first type because in the case of the cross-track, the satellite when captures the image and then returns after it, for example, hours or days later, captures the same place again. During this time may a large movement have happened in place makes the stereo vision have some defects, as changes occurred on the surface of the Earth at this time. While in the second method, long track, the time between the image and the next image in the same orbit will be small, so that the changes that occurred on the surface of the Earth has less effective on stereoscopic vision. This slide explains the method of creating a stereoscopic view through the across-track. We find on the left the satellite imaging in orbit in an oblique manner using the mirrors in the satellite, while in another orbit, it is imaging an oblique image and the track after it is a vertical image and the following image. Therefore, I can capture images from more than one orbit for the same place, and then, when we put two of them together, we can see a three-dimensional view. This slide is an example of how to make a three-dimensional image using the long-track method. In this method, the satellite, while moving in orbit, captures an image at an angle of 20 degrees to the vertical in front of it, then it captures a second time an image at an angle of 20 degrees to the vertical behind it. In this case, two images were taken of the same place, and each one of them is from a different angle. In this case, if we put the two images together, we can see a three-dimensional view. The beginning of satellites was with the American satellite Landsat 1 in 1972, and after that, the French satellite Spot 1 was launched in 1986. The first satellite, Landsat 1, uses the Whiskbroom imaging system, while the second French satellite, Spot 1, uses the Pushbroom system. Then, India launched a satellite called IRS-1A. Then, IRS-1B with a resolution of 72 meters and 36 meters. Then IRS-1C and IRS-1D were launched with a resolution of 5.8 meters. We will give a brief overview of three generations of satellites, each of which had an impact on the field of remote sensing by satellites. Landsat satellite. It is a series of American satellites, and it is the first satellite for remote sensing that orbited the surface of the Earth and used the Whiskbroom imaging system. A series of satellites were launched from Landsat sequentially, the last of which was Landsat 9 in the year 2021. The first satellite in the series, Landsat 1, was imaging with a resolution of 80 meters. The resolution improved in Landsat 4 in 1982 and became 15 meters for panchromatic and 30 meters for multispectral. In 1985, the program became commercial and provided data to civilian users. Since 2009, the Landsat image archive has been freely available online. The next satellite in the Landsat series is scheduled to be launched in 2030 and contains 26 spectral bands. The Landsat satellite will contain 9 sensors and can capture images in different ranges of the spectrum, such as blue, green, red, infrared, and thermal. The second generation of satellites, which is the Spot satellite, is a French satellite that was launched in 1986. This satellite is the first satellite that works with the Pushbroom system, and generations of Spot 1, 2, and 3 were launched, up to Spot 7. The Pushbroom method that the Spot satellite used in imaging is the one that is being used until now in remote sensing satellites. The Ikonos satellite is the first commercial high-resolution satellite available. It is the first satellite with a resolution of 1 meter and a radiometric resolution of 11 bits, and it can visit the same place within 1.5 days. There is currently a large group of satellites that visualize the Earth's surface in different ways and techniques from different countries. The following table shows the accuracy of a group of distinguished satellites in remote sensing. The table shows the number of panchromatic bands, multispectral bands, and spatial resolution of the panchromatic bands, multispectral bands, temporal resolution, swath width, radiometric resolution, the country and launch date of the satellite. The best satellite in terms of capabilities is number 11 in WorldView 3, as it can image in 8-band, meaning 8 ranges of the spectrum with spatial resolution, 0.3 meters panchromatic and 1.24 meters and multispectral, with radiometric resolution 11-bit, meaning it can distinguish 2048 degrees from degrees of reflection strength, and it can image the same place in less than a day, an imaging area of 13.1 kilometers width. Many countries launched satellites with different capabilities, including America, Taiwan, India, Japan, Korea, Germany, and China.